Alright, here's some example problems on the Doppler effect. A car is honking its horn as it drives past you. The people in the car measure the frequency of the horn to be 400 hertz. What is the highest and lowest frequency you will hear as it drives past you at 30 meters per second? Okay, so we've got our car traveling at 30 meters per second, and I'm standing right here. When the car is far away over here, the car is approaching me at 30 meters per second. When it's far away over here, it is going away from me at 30 meters per second. Alright, when it's right here, it's moving at 30 meters per second, but the Doppler shift is 0 because the component of velocity along the line between me and the source is 0. Alright, so I'm going to have a big positive shift here and a big negative shift here. Alright, the equation for the Doppler shifted frequency is just equal F, and then we have V plus, from the book it looks like this. Well, we look at this and we say, oh, okay, the velocity for the observer doesn't matter because there's the observer sitting still. But when we look at the source, we put a minus sign if the source is moving towards the observer and a plus sign if it's moving away from the observer. Alright? So when we're over here, when we get our highest frequency, we're going to plug in. So we plug in 400 hertz. And then we plug in here the speed of sound, which we'll assume is 343 meters per second. And then we have down here 343 meters per second. And then we're going to put a minus sign when the car is approaching us, 30 meters per second. And you plug that in and you get your answer. Alright? Now if you forget whether it's a plus or minus, just think, well, I mean, if the source and the observer are both moving, just kind of ignore one of them. Say, what if their observer wasn't moving? In this case, the observer really isn't moving. If I have the source moving towards the observer, should the frequency get higher or lower? It's approaching, the frequency should get higher. I need a smaller denominator, so I put a minus sign there. And that gives me my highest frequency. For the lowest frequency, when it's over here, I do the same thing. F is 400 hertz. And then I multiply by, the observer is still 0, so 343 meters per second. Then down here I have 343 meters per second. And now it's moving away from me, so I'm going to change the sign to a plus, right? And then I have my 30 meters per second. And this will give me my lowest frequency because I'm dividing by a bigger denominator. Alright, I'll let you plug the numbers in. A guy on the side of the street is playing a note on a trumpet with a fundamental frequency of 440 hertz. What is the highest and lowest frequency you hear as you drive past him at a speed of 35 meters per second? Again, right? F prime is equal to F times V plus V observer over V minus V source. And this is the sign we use when we're approaching. Alright? In this case, alright, the source is not moving. When I'm approaching, so before I reach where the trumpet player is, alright, I'm going to put a positive sign there, and I'm going to get 440 hertz times speed of sound, which we'll assume is 343 meters per second, plus 30 my speed, meters per second, divided by 343 meters per second, right? And that's when I'm approaching him. And when I approach, that's the highest frequency. Once I've driven past, it'll look like this. I have 343 meters per second for the speed of sound, but then I'm going to change the sign here because I'm going away, right? So the trumpet player is here, I'm driving away. So my velocity is in the direction away from the trumpet player. Alright? So I'm going to change this to a minus 35 meters per second over the speed of sound. Alright? And once again, when I'm going away, I expect the shift to go down. I have a minus sign in the numerator. That is correct. Okay, so now here's a really hairy problem, but it'll turn out not to be hairy once we just understand how to do it. You're swinging on a swing. If you define the plus x direction to be in front of you, your x component of displacement on the swing as a function of time is given by a sine at. A speaker mounted on a spring is directly in front of you, but a long distance away from you. It is playing a sine wave with a frequency f. It is oscillating back and forth with its displacement given by b sine bt plus c. Alright? So A, B, B, and C are all just constants. Okay? Now why is it important for the speaker to be far away? Well, if I'm sitting here oscillating like this and the speaker is oscillating here, remember it's only this component of velocity that matters. But if the speaker's really far away and I'm, awesome like this, it's like we're in line, all right? And so I can just pretend like my ears and the speaker are just in line with each other, all right? And then I want to find an equation for the frequency you hear as a function of time. So I have my Doppler shifted frequency again. It's just f v plus v observer over v minus v source, all right? So I just need to know what v observer is and v source is. So v observer is me, right? So I take the time derivative of this and I say v observer is just going to be a cosine at, right? And that's the velocity of the observer. Now notice, if I'm moving in the plus x direction, the spring, the speaker on the spring is in the plus x direction away from me. So if I am moving in the plus x direction, that means I'm moving towards the speaker. So my velocity here is going to be positive, all right? So that's perfect. So that's what I plug in for v observer. For the speaker, I take the time derivative of this, and I get the velocity of the speaker is going to be b cosine bt plus c. But then I think about this and I say if the speaker is moving in the plus x direction, that's moving away from me, right? And that sign, this thing right here, is positive if the source is moving towards the observer. So I'm going to plug in put a minus sign in here, all right? Because I don't care about the x component of the velocity. I care about the component either in the direction approaching the observer, all right? So I plug these into the equation. F prime is equal to f times v plus v observer, but v observer is just a cosine at. I divide by v minus v source, but I've got a minus sign right here, so it's going to be b cosine bt plus c. All right? So now, I can check my work. First of all, the units work out, right? A has to have units of meters. Little a has units of, that's a frequency, right? Inverse seconds, an angular frequency. All right, so it's meters per second. Okay, that's good. That has units of velocity. All right, but let's take some cases where I know what's going to happen. Okay, if I'm not moving and the speaker's not moving, we take the limit of our amplitude going to 0, we should get the undoppler shifted frequency. That works. All right, now imagine that the speaker and I are moving at the same velocity, or with the same velocity in phase with each other. So let's say that this c, this phase shift c, is 0. Let's say we're both going at the same frequency and we have the same amplitude. All right, that means the speaker and I are moving together, all right? And the effects of the Doppler shift should cancel out. And in fact, that's what happens, right? And so it looks like I have the sign correct here, right? This minus sign here, I got that correct because if the speaker and I are moving, in sync with each other in the same direction, then I shouldn't get a Doppler shift, and I don't, all right? But if the speaker is moving in the opposite direction from me, if there's a 180-degree phase shift, then I should get Doppler shift. Anyway, those are the problems I have for you.